We are the Gujarat Technological University. Since its inception over a decade ago, GTU has been empowering young and curating minds to realize their true potential. Over 4 lakh inspired students are enrolled with one of the premier academic universities in India. With more than 450 affiliated colleges in its fold operating across 5 zones of the state, GTU, the International Innovative University, your place to move forward.
Welcome you all. Today I am going to deliver a session on AC voltage controllers, which are also known as AC regulators. So first of all, let's discuss what is AC voltage regulator and the requirement of this converter. AC voltage controllers converts fixed AC quantity to variable AC quantity by keeping the frequency constant. Now, the question arises that if we are not going to vary frequency, then variable AC output can also be achieved using tap changing transformers or auto transformers. And also, the quality of output AC voltage is also better compared to AC regulators. Then, why we require AC regulators? For example, we want to control the speed of AC motor using transformer, and the required variation in speed is 1400 rpm, 1410 rpm, 1412 rpm, 1413 rpm, etc. Such a precise and smooth control cannot be achieved using transformers. Also, as the rating of transformer system increases, the size of transformer also increases. And as the rating of transformer increases, the copper losses in transformer also increases. Now, if we want to control speed using AC regulators, then we can achieve precise and smooth control because AC regulators use power semiconductor switches with a digital controller. The system developed using power semiconductor devices is much smaller compared to same rating of power transformer. It is to be noted that above all discussion with comparison to transformer is just to understand the requirement of AC regulators along with some compromise in power quality. Therefore, AC voltage regulators are suitable for some specific applications like lighting control, industrial heating, resistance welding, on-load static transformer tap changers, as well as speed control of induction motor. Now, these are the methods of voltage control in case of AC regulators. The first method is integral cycle control and the second one is phase control. Integral cycle control is also known as on-off control, in which we connect the source to load for few complete cycles and disconnect it for few complete cycles. This kind of control is suitable for the systems with large time constant. Whereas in case of phase control, we control the output voltage by changing the firing angle. And this kind of control is suitable for systems with a small time constant. We will discuss both the methods in detail. So first one, integral cycle control. As I explained, in this case, we have connected the AC source with load along with anti-parallel connected thyristor pair, in which we turn on and off both the thyristor for few complete cycle and turn off for few complete cycle. For example, N is the number of cycles to be kept on and M is the number of cycles to be kept off. Then the duty cycle in this case can be calculated as duty cycle equals to N number of on cycles divided by M plus N number of total cycles. In this type of control, the average power to the load can be varied from 0% to 100%. Now, these are some types of gating signals which we can provide to our AC regulators. The first one shows a single pulse, The second figure B shows a continuous pulse, and the third figure C shows a pulse train. Now, where these are the pulses, different type of pulses, where to apply to which kind of pulse. So, if we are using a resistive load, then the first single pulse is sufficient to turn on the thyristors. But if we are going to use inductive load, RL load, then a continuous pulse or pulse train must be applied to keep the thyristors turned on. Let's discuss a single phase half wave voltage regulator. This circuit is also used to explain the principle of phase control. In this case, the AC voltage source is connected to the resistive load through a thyristor and a diode connected antiparallel to each other, in which thyristor T1 conducts during positive cycle and diode D1 conducts during negative cycle. As we can see here, we can have a control of firing angle alpha through thyristor only in positive cycle, and we have a diode during negative cycle, so we cannot control turn on and off in negative cycle. Therefore, this particular circuit is known as half control or half wave voltage regulator. If we replace our diode through thyristor, then both the thyristor can act as a positive and negative cycle controller using the firing angle alpha. So we can have a complete control if we use single phase full AC regulator. This slide shows some another alternate forms to create AC regulator, in which the left circuit shows a diode bridge connected to a load with a single thyristor, in which during positive cycle diode D1, thyristor T1, diode D3 connects to the load, and during negative cycle diode D2, thyristor T1 and diode D4 connected to source, load to source. In the right side circuit, we have replaced the entire diode bridge with only triac, which can also serve the purpose of control in positive as well as negative cycle. This shows a full bridge AC controller, AC regulator with resistive load and the waveforms. The first waveform, upper one, it shows that supply waveform. The second waveform is pulses given to thyristor T1. As we are using resistive load here, we can apply a single pulse to turn on thyristor T1 as well as thyristor T2. The second figure shows pulses applied to thyristor T2. Next waveform is the output voltage waveform, in which thyristor T1 turned on at omega t equals to alpha and thyristor T2 is turned on at omega t equals to pi plus alpha. As we are using resistive load, the output voltage and current waveforms are identical to each other and completely in phase with each other. So E0 and I0, output voltage and current waveform, are almost same. The last two waveforms are thyristor output voltages VT1 and VT2. This particular slide shows the single phase AC regulators with RL load. If we replace the circuit with RL load, then there is a phase difference, say phi, between voltage and current due to presence of inductance. So if I select my firing angle alpha, which is less than this difference, less than phi, then there won't be any effect of firing angle in the output voltage and output current. As you can see in the figure C, if I am selecting my alpha less than phi, then my input voltage and output voltage are exactly same, and input current and output current are exactly same. So to get the effect of firing angle alpha, or to get the control of thyristor T1 and T2 to output voltage, we must select our alpha greater than phi. So figure number B shows alpha greater than phi waveforms, in which you can see the output voltage is turned on, मतलब thyristor T1 is turned on at omega t equals to alpha, and it continues to conduct even after voltage is 0 due to presence of L, and it is turned on at omega t equals to pi plus alpha. Thyristor T2 is turned on at pi plus alpha, and the last two waveform shows VT1 and VT2. To improve the power factor and reduction in harmonics in the source and load current, we can improve the control, or we can improve the sequence of control, which is also known as sequence control. Two or more stages of voltage controllers are used in parallel for this type of control. Parallel voltage regulators are triggered in a proper sequence to get desired output. Sequence controlled AC regulators are also called as synchronous tap changers or transformer tap changers. This slide shows the circuit of two-stage sequential control in which AC voltage source is connected to a primary to transformer and secondary of transformer is connected to load through two pairs of anti-parallel connected thyristors, in which we have two different stages of output voltage, E2 and E1. So, in this case, first of all, thyristor T3 is turned on. Therefore, the positive output voltage first we will get as E2, and then thyristor T1 is turned on. So, the output voltage we will get as E1 plus E2. So we have two different stages in output voltage. First stage is E2 and second stage is E1 plus E2 in positive cycle. Now, if we talk about negative cycle, then first of all, thyristor T4 is turned on at omega t equals to pi, and thyristor T2 is turned on at omega t equals to pi plus alpha. Then we will have two different stages in negative cycle as well, minus E2 and minus E1 plus E2. This we can see from the waveform. As we can see from the waveform, thyristor T3 is turned on at omega t equals to 0. Therefore, the output voltage magnitude we get as E2, and at omega t equals to alpha, thyristor T1 is triggered, so the output voltage is E1 plus E2. If we consider it as Vs and twice Vs, then E2 should be Vs and E1 plus E2 should be twice Vs. Same happens for the negative cycle. At omega t equals to pi, thyristor T4 is turned on, and at omega t equals to pi plus alpha, thyristor T2 is turned on. As we discussed earlier, in case of R load, both the current and voltage waveforms are identical. For positive half cycle, firing angle for T3 and T4 are always 0. At this range, firing angle for T1 and T2 vary to get output voltage in the range Vs to twice Vs. As T1 fires, output voltage becomes E1 plus E2 or twice Vs. This particular slide shows a two-stage AC regulator with RL load. Here, the firing sequence is almost same as R load. At omega t equals to 0, thyristor T3 is triggered or turned on. At omega t equals to alpha, thyristor T1 is triggered. And the notch we are observing here is due to the presence of inductor in the circuit. The second waveform shows the current waveform, and the upper one shows the output voltage waveform. In this case, the switching pattern is same as R load. At omega t equals to pi, output voltage V0 is 0, but current is non-zero due to the load inductance. T1 continues conducting to an elapsed angle by extinction angle beta. At beta, T1 is turned off. At omega t equals to pi, T4 is fired, but from the point pi plus beta to pi plus alpha, output voltage V0 remains Vs. T2 and T3 won't conduct simultaneously, so there won't be any threat of short circuit. We can also achieve multiple stage sequence using power circuit in which a back-to-back connected thyristor pairs can be used at the secondary of transformer to get a different stages of power control. As stage increases, power factor also increases and harmonics are also reduced using multi-stage sequential control. Transformer has n secondary windings. The secondary winding voltage can be calculated as Es divided by n. The voltage at any node P with respect to K is Es. Voltage control from n-3 Es by n to n-2 Es by n can be achieved by controlling the firing angle of switch pair 4. Output harmonic content is proportional to magnitude of voltage variation. Thank you all.